Hello there, and welcome to the Chapter 7, Lesson 7 notes on exponential growth and decay. Remember that exponential growth is where the graph looks like this, and exponential decay is where it looks like that. Aw, sad day. Okay. By the end of the day, you'll be able to model exponential growth and decay in word problems. First, let's review modeling situations. If you have a starting amount of $100 and then you earn $2 per day, that means you're going to match with this guy right here. Think of it as like 100 is your y-intercept and then 2 is your slope. You earn 2 times each day. Cool. Now let's flip it. You start with $2. And then you earn, I changed that. You start with $2 and then you earn 100 each day. I prefer this one because you're earning more each day. So you'll catch up super fast, like literally in a day. So that's nice. And that guy matches up with this guy down here because now our slope is 100 and our intercept is 2. But let's say you begin with $100, but then each day the money doubles, so it's 2 times that amount of money. That's going to be exponential. Your initial is 100, but your growth rate is 2. So you get 2 to the power of however much time passes. So that gives us our last guy right there. Throwback to exponential growth. Yesterday we talked about y equals a times b to the xth power, where a is going to be greater than 0. As long as a is greater than 0 and b is greater than 1, then you are going to grow. Then it is going to get bigger just like this. It's going to get bigger just like this. Okay. Here is a little review. Remember that we call B the base, and that shows you how quickly something is growing. The technical term is the growth factor. Earlier we called it the rate. It's the rate at which it's growing. We also spelled rate correctly. It's the rate at which it's growing. Okay. Our A here, A is our initial value. It's where you start. It's where you initialize. It's your starting point. It's where x equals, not x equals 0. It's what x is. No, I lied. Yeah, it's x equals 0. It's your y-intercept. So here, A right there, and B is how much it's growing by. Okay. So let's say that in 1985, there were 285 cell phone subscribers in a certain town. The number of subscribers increased by 75% each year after 1985. Our initial value is whatever we start with, so we start with 285. Our growth factor describes how quickly it's growing, but our growth factor here is not 75%. It's not even 0.75, namely because they're the same thing, but it's increasing by 75% each year. That means you start with 100% of what you have, and each year you're adding 75%. So our growth factor is 175%. Or if you like decimals, that's 1.75. And our exponent is always x. So if we're going to follow the pattern, y equals a times b to the xth power, then that's going to put us in y equals 285, because remember our initial is represented by a, our base is represented by b, times 1.75 raised to the power of x. Yoink, yoink. X is always our exponent. So how many cell phone subscribers were in the small town in 1984? Well, that's going to be for where x is the year after 1985. we need to figure out, shoot, okay, how many years after 1985 is that? 1994 minus 1985 will give us 9 years. So x equals 9. Okay, so we plug this all in. We know our time is 9. Wink. And to evaluate this, do your exponent first. So you need to find out what is 1.75 raised to the 9th power. Then make it twisty diagonal for some reason because you glitch. Anyway, you multiply that out, you get 43,872 people. Isn't that great? So fun. So that's an example of exponential growth. Let's talk about a more common example. Besides like population growth, you also have something that's very interesting. It's a certain kind of interest. Interest is something that you get on a loan or when you deposit money like in a bank account. Compound interest is interest that's put together. It's interest earned on the principal and the interest on the account, according to what's already in the account. So basically what happens is you have a certain amount of money in your account. Okay, let's say you have this much money, and then you earn a little bit of interest on it. Then on your next time, you have that much. But instead of just, so if this is like, that's the original amount that you invested. And then each time you earn a little bit of interest, a little bit of interest, a little bit of interest. It's not linear like this because you earn interest on the interest each time. So it gets way bigger. That was a terrible drawing. But anyway, it's the initial amount we call the principal with a PAL. Principal with a PLE is an idea. Fun fact, that's not what we're talking about right here. The amount of money deposited in the account, that's how much you have at first. And then simple interest, which is what we're not talking about here. Simple interest is what happens when you only earn money on the principal itself. Here we're earning money on the interest as well. So, Lauren deposits $1,200 into a bank account, paying 1.25% interest compounded annually for 5 years, at which point the account holds that much. Well, we have a lot of information here. Let's break it down. Principal is the amount that she invested at first. That's $1,200. The time in years, that's going to be basically our X value. That's 5. The interest rate, rate. I should have made this red because that's like our growth rate. Our interest rate is 1.25%. To put that as a decimal, we're gonna move the decimal point over twice. Bink, bink. Ta-da! So that's 0.0125. And then the balance, the amount we get at the end, is going to be equal to our y. It's 1276.90. Okay, cool, but you don't know what to do with this. So I'm going to give you the formula now so we know where to go from here. So this is what happens. First, we need to start out with our principal. We're going to represent the principal with, wait for it, P. Okay, because that's our starting point. And then we need to look at our rate. Our rate is going to be represented by R. This is going to be like, so this is like your A. This is like our B. The number of the times the interest is compounded per year, we're just going to represent that with an N, and that will That will come in handy later. And then finally, like our x, we have our time. We're going to represent this with t, the time in years. And then finally, the result will be the amount in the account. So we present it with A. You can decide if A stands for amount or account. It doesn't matter. Either way, A is going to be equal to, well, let's just take our exponential growth formula, right? Typically we have A times B raised to the xth power, right? Because that's exponential growth. But instead of A, we have a P for principal. So P, very exciting. And instead of B, we have an R for rate. But remember back here when we talked about our population, we needed to add 100% to it because it's growing. We take what we already have and we add to it. So this 100%, this 100% right here, remember that's 1. That's why we got 1.75. We need to add a 1 to our rate. So instead of B, we have 1 plus our rate, which is R. Cool, huh? Isn't that great? But sometimes our interest is compounded more than one time in a year. If it's compounded quarterly, that's 4 times in a year. If it's compounded monthly, that's 12 times in a year. So we actually need to take our rate and divide it by n, the number of times it's compounded per year. Since we have time instead of x, we're going to change that to a t. And since we're multiplying it, or I gave it away, I'm so sorry. Since we're compounding it multiple times during a year, we need to multiply that times our time. So we get this formula right here. The amount is equal to the principal times 1 plus your rate divided by how many times, the number of times per year it's compounded, and parenthesis, all raised to the power of the number of times the number of years. Beautiful, huh? Guess what? You get to memorize this. So know it, love it, cherish it, remember it forever. But I have a special hint for you. If you can't really remember this, I have a word, one single word for you to remember this formula. Are you ready? Here it comes. The word is apparent. I love my job. Okay, well, anyway. So when Ryder was born, his parents deposited $2,000. Right away, you should say, oh, that's my principal. Awesome. And an account paying 4.5% interest. Guys, that's really good. If you like that, that's amazing. That's an excellent interest rate. Holy cow. Compounded quarterly. Remember, quarterly is 4 times a year. Because there are four quarters in a year. What will the account balance be after 18 years, after time has passed? Well, let's remember our compound interest formula. Remember at per 1 or Let's take our formula and let's fill it in with what we know. Well, what do we know? We know the principal is $2,000. Ta-da! Do we know the rate? We do. The rate is 4.5%. So we need to express that as a decimal, 0.045. We know it's compounded quarterly, so number of times per year is 4. And we also know the time is 18 years. So there we go. Now we just have to figure out what is 2,000 times 1 plus 0.045 over 4, all raised to the power of 4 times 18. Well, I will let you figure that out. Come back when you get it. It's approximately 4475.53. So let's zoom out and look at what that means. When Ryder was born, his parents deposited $2,000 and they didn't touch it for 18 years. It's not like Ryder went out and earned more money, but no, it more than doubled just sitting in an account for 18 years. Guys, invest your money right now. Talk to your parent, like pause this video. Talk to your parents about, do I have a banking account? Can we start a savings account? Because seriously, save money and the bank will literally pay you to put your money in the bank. Like there's no reason not to. Okay, so we've talked about growth. Let's talk about decay real quick and then we'll call it a day. So we can still use our a times b to the xth power, but we're going to still keep that a is positive. But if b is less than 1, but it has to be greater than 0. So if b is between 0 and 1, then that's decay. Then it will go down like this. In this case, instead of being called the growth factor, b is now the decay factor because it's ungrowing. Since ungrowing is not a word, we'll call it decay. Okay, so our rate of decay is our decay factor. So let's say, in a sad twist of fate, you have fish that are dying off, rip. They decrease by 6% annually. This does not mean that our decay factor is 6%, but we'll get there. In 2015, there were 50,000 fish. So, how can we represent this population? Well, let's start with our y equals a times b to the xth power. Remember, a is going to be our initial amount, b is our rate, our decay factor, and our exponent is just always x. Or you could have made it t if you want, t for time. I'm just going to make it x. Okay, we'll say x is years after 2015. Okay, cool. So our initial value is 50,000 fish. Our decay factor is not 6%, because if it decreases by 6% annually, you take your normal amount, you subtract 6%, and then the next year you are left with, I almost said 49, you are left with 94% of what you had originally. So your decay factor is 94%, or 0.94. Ta-da! Okay, now let's take that information, plug it into our formula. We get y equals 50,000. Why did I write such a long number? I don't know. Times 0.94 to the power of however many years we have. X. Sure. Sweet. So what will the population be in 2030? Well, 2030 is 15 years after 2015. So we need to make 15 our x. So give us to the 15th power. Plug that in. It comes out to approximately 19,764 fish. So after 15 years, we have less than half of the fish left. Rip. Well, there you go. That's exponential decay. That's exponential growth. Notice that they're basically the same thing. It's all a times b raised to the xth power. And that's what compound interest is. It's a times b raised to the xth power. It's just a little bit more specific. And by a little bit more specific, a lot more specific. Anyway, know it, love it. Have a great time on your homework.